Hello everyone, welcome back. This is lecture 9 of our computer vision course. Today we're going to introduce the CAM, attention, and transformers. More specifically, we're going to introduce the datasets for deep learning, the CAM, attention, and self-attentions, and transformers. We already seen in last lecture that deep learning and deep neural networks make it easy for us to build complex models by just stacking layers. However, in machine learning, the more complex a model is, the more data it needs. So to train those complex models, we need a huge amount of data. Especially, we need the data to be labeled. However, the labeling process itself is a costly process because it takes time and take a lot of efforts, need a lot of people. Sometimes we need the experts as well. Fortunately, there are some datasets are publicly available and they can be great help. ImageNet is the one that most people started with, and you will see here we got a lot of images in ImageNet, and there are many classes there as well. Even those images are not with very good quality because most of them are with low resolution. However, it's a huge amount of images you can play with. There are actually a lot of people and groups are working on that datasets. Here is a website called Paper with Code, where you can check the latest performance on that datasets. As you can see here, and the top performance right now is code at 97, and most of those are usually come with the source code and a paper with them. So it's a place then you can learn what's happening there and what's the problem issues in that data sets or models. And by checking out those results, it will help you to learn and improve your models as well. As I mentioned, the ImageNet with images of low resolution, and another alternative is CIFA. CIFA are with images with better quality, and CIFA has 100 version. That means there are 100 classes of that data sets, and there are something like 60,000 images with better quality. And there is a subset of it called CFR10. A lot of people start with that, in which you have less images and less classes there and easier to start. Here are the latest performance on CIFA, and you could see the top performance right now is the efficient night L2, and followed by the WIT. WIT stands for Vision Transformers, and we're going to introduce Vision Transformers today. In addition, there is COCO. COCO is another dataset which you can use it for image detection or image segmentation. We will introduce what they are later. There are more images there you can see, and also we have ADE20K, and there's another data set with different types of images in different scenarios, but also for image segmentation. Well, due to time limitation, I can just give some examples for those data sets. There are definitely more of them there. If you're interested, you can check it out, but I think those are more than enough to help you to start. Great. Now we can build complex models by stacking layers, and we have huge data sets for training. And to start the experiment, there's one thing we need is we have to tell how actually the models are working. So because most of the time the development process is like trial and error, we have to know where we got wrong and where we got right. So it's quite important. In the tutorials, we've already known that we can evaluate the performance of model with something like accuracy, precision, and recall. However, those are just statistics about the overall performance of our model, and we can't tell exactly how it works actually, especially in um, deep learning. The reason is the deep learning and deep models are usually considered as a black box. The reason is no matter in traditional machine learning or deep learning, we're actually learning a function f, which can map the given x to the labels we want y there. So we're learning a function there. However, in a traditional machine learning, f is given is something we know, and we can do a lot of analysis using our mathematics knowledge, so we could figure out a better f in between. However, in deep learning, it's an advantage that we don't have to know what the f is, but at the same time, it's a disadvantage. We can't run analysis on f because we don't know what exactly it is. So it's considered a black box. Fortunately, for things we don't know from inside, we can use some probes to test it so we can understand it from outside. And we have some kind of tools like that as probes. The class activation mapping is one of them, and sometimes we call it CAM in short. The idea is let me draw the framework of CNN for you for easier understanding. Let's see, we have an input, which is an image. Then it goes into the convolutional layer, layers by layers. We are supposed to have a lot of them. Then, and after the convolutional layer, we have the FC layer, and this is convolutional layer, and it gives us the output. Here are two things we can use. The first is the result of the convolution. Usually it's a feature map. It's composed of a lot of neurons there. The larger activation means the higher response of corresponding neuron. So it contributes more for the inference later. So usually, the spatial dimension are preserved in the feature map. That means it can be resized back to the original image. Let's see if there is an airplane in that image. And there are supposed to be some of neurons are corresponding to the airplane. So those neurons are supposed to have higher response if we are predicting something like an airplane. This is one information we can use. That means the feature map itself tells about the responses or activation of those neurons, which we can check it out if the network is focusing on the right part of the original image. This is one information we can use. However, the other thing is usually in the feature map we have multiple layers. Each of the layer may capture different types of thing of that original image. It's like we have RGB channels inside that original image. So each of those are probably some of the feature the channels focusing on the sky, some of that channels focusing on the airplane, or they work jointly to focus on the airplane. So in this case, we have to fuse those channels. Those are channels. Um, uh, to fuse that channels, there's another thing or another type of information we can use, which is because the convolutional layer is connected to that FC layer, and there are there are a lot of weights on the connection because each of that channel is composed of neurons as well, and those neurons are connected to neurons on the FC layer. The higher weights, the greater weights of the connection, the more contribution of that neuron. So we can summarize the contribution of neurons through all the weights they're used for build a connection. In that case, we can summarize the contribution over different channels there. So there is a summarized, for example, we can take the um, average of those weights for this channel, and we can take another average for this channel and another average for this channel. Then after this, we can fuse the feature map, use a weighted average, summarized average. Um, then we have a final feature map as a heat map, which can tell us which parts of that feature map contributes more. Because the feature map, as I mentioned, the spatial dimension are preserved in the feature map, so it can be resized back to the original one. So we will have the final heat map tell us which part are focused more than others and which part are contributing more than others there. Here is the first implementation of CAM in which the author actually insert additional layer in between the last convolutional layer and the first FC layer there. The average pooling will calculate the average of the connection weights, then use that weights to do the thing I mentioned, to fuse each of the channel into a single feature map there. And you could see each channel actually focusing on different parts. And here it's on that person, here it's on that dog. So after the fusion, it will generate a final feature map, and which can be recessed back to the original image. You know where the network is focusing on. Here are some of the results which showing where the network is focusing on. For example, for predicting the hands, it focuses on the hands very well. For predicting the barbells, it focuses on the barbells very well. So this is with great help because we know how is our model are working properly by checking out the CAM. However, as mentioned, the first implementation of CAM actually need to insert an additional layer in between the last convolutional layers and the first FC layer. So that need to modify the original architecture of the neural network. So in most of the cases, it's not feasible. So here comes another um, um, CAM called Grad-cam. Grad-cam doesn't have to refer to the weights, rather it's assumed that the gradients on each of the map tells the information where the network focuses more. So the thing the Grad-cam is doing is every time you have the prediction, you use the back propagation to get the gradients on the last convolutional layer. So this layer, you can do this for each channels as well. And then we can take the average of the gradients of each channel as the weight for it. So we use the average, the weights to fuse different channels. Then it will tell you some information like that. So it's a heat map as well. By doing this, you don't have to modify the original architecture of your neural network. So it becomes more feasible. Grad-cam is really popular because you don't have to modify the architecture. However, it has its own problems. that is, the gradients are usually come with noise and unpredictable changes there. Those will make the final result unreliable. To address this problem, here comes the score-cam. Score-cam doesn't have to refer to any gradients or weights. Rather, the gradients is with the assumption that like if a channel focuses on the right part, it will lead to the better prediction than others. So what ScoreCam is doing have two stages. In stage one, we input this image to CNN as we are doing so far. Then we have feature maps consists of different channels there. Then in stage two, um, it will take out each of that channel as a filter, a mask, and apply them back to the original image. Let's see, this channel is focused on the feet of that dog. Then after using it as a filter on the original image, we will have an resulting image which will make the feet more salient than other parts. And the second channel you see it's focuses on the head or the body of that dog. Then after the filtering, this part will be more salient than others. Or if it's focused on the wrong part, like the background, the background will be more salient than others. So compare back those two different resulting images. We know that those two are focusing well on the dog, and this background one is not. So we can input them, each of them, into that scene and separately to make a prediction. In case that it's focusing on the right part, it will make a better prediction. In case, for example, this background channel doesn't have the right focus, it will not make a good prediction at the end. So we can use the prediction as the weights indicator to fuse those channels. Then it finally will be linearly combined into a single heat map as the final result, and telling which part the neural network is focusing on. By doing this, you see that ScoreCam doesn't have to rely on any of the gradients or weights, but rather it's purely based on the forward result. So make it more convenient and feasible in a lot of scenarios. There are a lot of variants of those CAM methods actually, but due to time limitation, we're not able to introduce all of them. However, we actually have done some work on the CAM by ourselves. It's called conceptor-CAM, and I would like to introduce it here a little bit. What we have done is we found in any of the CAM we have introduced, they are actually fusing channels. In that case, they're considering the contribution from different channels. However, they ignore there is contribution difference inside each of the channels. That means each part will contribute in different way. So we take that into our consideration to generate the conceptor-CAM, which will jointly consider the channel distribution and the internal channel distribution at the same time. So it will lead better results. Another thing we're doing is actually we consider there are both positive evidence and negative evidence, their contribution should be evaluated differently. For example, here might be the positive evidence for making the prediction. However, the sky, the lawn, might be references or might be the negative evidence for making the prediction of that parachute. So we have proposed a way to use them jointly. I mean, the positive evidence and actually the pseudo-negative evidence together, so we can make better CAM at the end. And here are some results, and by comparing them to different CAM, actually this is a framework rather than a specific CAM method, so it's compatible to previous CAM. You could see here we can use it together with the Grad-cam to generate better result than the Grad-cam, and we can use it with the layer cam and generating better result than our original layer cam. Okay, right now we can see if the network is focusing on the right part. However, beside we know that result, can we help in between to guide that model to focus on the right part? Here is the attention mechanisms. Attention is something like we can add filters in between those convolutional layers. The idea is something like we can, let's see, here are some convolutional layers, and we can make a mask there which has the equal size as the feature map. So if we in case we want the feature map focus on some of that part of that feature map, and we can give higher weights on this part, and we can give less smaller weights on the other parts. So that feature map will be augmented by this mask or filter. For example, here we are putting some mask on layer 10 to help them to focus on the frog, or focus on the deer, and the airplane as well. So because by doing this, the network will pay less attention on those background parts and focus on the right parts, and hopefully we can make the final prediction more accurate than not using the filter. And this is actually quite straightforward. However, it's not easy if we have to define this mask by ourselves. But fortunately, because we have the backpropagation, we can have the neural network figure this out automatically with the backpropagation, because those are just weights. I mean, each of the components on the mask are just a weights, and weights can be figured out by the backpropagation and automatically updated by the backpropagation process, because finally the partial derivative will be passed back to that weights as we have learned previously. So in that case, what we have to do is just set a filter, a weight mask there, and we use the backpropagation to figure out that weights. You could see these are actually the results of the mask. It's focusing very well on the correct part at layer 10. But actually, in the original implementation, you could see it's actually using applying the mask at different layers of the original neural network, and finally you should be able to have better result as predictions. And this is a basic idea of attention mechanism. However, you could see from here the weight are putting on the spatial dimension there, because as we mentioned many times, the spatial dimension of the original image are actually well preserved in the feature map. That's the reason if we can apply the the filter at the spatial dimension of the feature map, the corresponding part will be augmented than other parts. I mean, corresponding to that part. So this is the idea of attention mechanism, but right now it's on the spatial dimension. And actually, besides doing it on the spatial dimension, we can actually do it on the channel dimension as well. Here, the CBAM, called the convolutional block attention module, can do that. Actually, it has considered both the spatial dimension and the channel dimension. And this part is actually the same. Here is the spatial dimension feature map can be figured out by the backpropagation. And here is a channel dimension giving a weight for each of that channels, which can also be figured out by the backpropagation. So in CBAM, here is an overview of it. It actually apply the channel dimension first, then apply the spatial dimension there by combining the result augmented by both the channel attention and the spatial attention. It will have better result. That makes this method also really popular. However, no matter it's spatial attention or it's the channel attention, they're using the backpropagation to figure out the result. That means the result, the weights of those attention are actually determined by the final prediction. However, there is a group or method that's very different from them. This is actually called self-attention. It's an idea from the NLP domain. That means the natural language processing domain. So I think to understand it better, we can see a sentence because it's from NLP. This is a CV course which is cool. So you know that each of the words can be represented as a feature vector as well. There are a lot of methods can help you do that. Anyway, it's a feature vector. Let me write down each of them as a feature vector. And I don't want to draw more. So, and those are vectors. And you know that in this sentence, some of words are actually interconnected. Like this actually is referred to the CV course, and also the cool thing is the CV course. So those words are interconnected, more tightly connected than others. So in that case, we can calculate for each word its correlation to other words. So because this is actually interconnected to the CV course, so this connection will be stronger than others. Their correlation will be greater than others. And at the same time, this will have a stronger correlation to the feature vector of cool. So the correlation will tell something that some of the other words may contribute to the original words. So we can use them as an argumentation. For example, let's see, here is the weight 1, weight 2, and the weight 3, and weight n there. So we can use, we can summarize this kind of contribution by doing something like we put the correlation as a weight and multiply by that vector at the ith place, the ith words of that sentence, and we can put them as a new representation. Let's see, the V star for certain words. So if it's for the first words, and a new vector will be generated to the first words. So in this way, repeating that process, you can repeat this process for different words. For example, you can calculate the correlation of the second words to the other words in that sentence and generate a new version of that representation for vector. This is vector 1 star. This is vector 0 star. And you can repeat that process. So you will see here, by doing this, some of the interconnected words will serve to argument as an argumentation for generate representation for their correlated words. So in this case, we are those are like the attention from the sentence itself. So that's the reason it's called self-attention. But now you might be wondering, like why we have the Q, K, and V, what they are. It's actually, again, let's rewrite that sentence again. So this is a CV course, which is cool. So let's see, in previous example, I'm just using one feature vector for each of the words, but in reality, we can use 3 of them. Let's see, this is the Q, and we have another for the first one, K, and we have another V. So let's see, for each of them we have 3 words. The reason we're having that setting is because sometimes one word will be used as a query words. This is Q stands for. Sometimes it will be used as a keywords. Sometimes it will be used as a value. That's the 3 letters stand for. So in natural language processing, it happens a lot. We are using it as a query to search the keywords, and the keywords will be mapped to a set of values. Like in the Google search engine, you type in a set of words, that's a query, and the search engine will compare your query to the keywords they have on each of the documents. And then inside the documents, there are more value there, and there are more words in that documents there. So by distinguishing these 3 different rows of words, it can calculate the correlation in a more decent way. Or so that is the reason why we have 3 feature vector for each of them. So by this setting, we can actually, when we are calculating a new representation for words, what we can do is actually repeat the same process we have demonstrated previously. We use the query to calculate the correlation to another keywords. This is like in the search retrieval process, we are compare the query words to the keywords of that document and see how related the query is to that keywords or to that document. But finally, we will return the value of that document. Anyway, right now we can calculate the correlation for each of the representation, but this time to the keywords, not for the query directly. After the calculation, we will generate a new representation for the first words. In that case, we will use the correlation as a weights for the value rather than to either Q or K. So this correlation will be applied on the value representation, the value feature vector for each of the words to generate the new representation at the second round there. So this is the reason that we have the Q key V, and here you could see actually this is the part corresponding to where this part in which we're calculating the correlation of query to keywords. And then after that, we will use a softmax to regulate those correlation to make them range put them into range of 0 and 1, and so they can be used as weights to as argumentation for the value words. So this is corresponding to the parts that once we have the value, we create a new representation for each of the words using that as a weights. And this is the self-attention parts. So that's the reason you have this self-attention by representing them into a figure. It will be like we calculate the correlation between the Q and the K. And finally, we use a softmax to regulate the weights. Then we multiply them back to the value words representation of each word to generate a new one at the end. So this is called self-attention. It's from the NLP domain again, as I mentioned. However, you have already seen that actually in vision domain, we can represent each of the image as visual words as well. In that case, we will have something like this. So each of the patches, this is simplest way. Each of the patches are actually one visual words, or even we can extract local features at the visual words, or even we can take each of the pixel as one visual words. So in the same way, we can generate representation for each of these visual words, and we can calculate the query words, the correlation between the query words and the keywords. And we can also use the linear combination by adopting the weights, the self-attention weights there to generate representation for each of them. You will see here, our set of results and showing the self-attention will help you to focus on the right part of that image. So this is self-attention, and which is kind of different from the attention mechanism we have introduced previously in the CNN. And with self-attention, people have proposed a really successful model called transformer. Transformer is doing something like you. Let's talk in the NLP domain. It will be more intuitive here. We have a sentence. Say this is a CV course. So this is English sentence, and transformer are originally proposed to do something like they call sequence to sequence mapping, because the sentence itself is a sequence of words. And if, for example, if we're doing the machine translation, we have to translate them into Chinese sentence, like something like that. We are translating this sentence, this sequence into that sentence. So what transformer is doing is taking each of them, each of the words as a token, and like what we have shown previously, and using the self-attention to generate representation for each of that token. So finally, you will have a set of feature vector as a token representation for each of that words. Then we will input each of that words. This self-attention process can be used for n times there. You can repeat that process. And then we will use that each of that words as an input for the decoder part. By the way, this on the left called the encoder part because it's encoding those words into vector representation. And in the decoder part, we have to decode the feature vector into words. So in that case, we will use this as an input to there, and for each of them, we can decode one words. And if everything goes right, the first words we should have is this, because it's a correspondence to that English word. And then after that, we will take that output as the input here for the decoder, and at the same time while taking the next words as the input for the encoder as well. So you starting from there, you could say there are actually two inputs. One is the feature representation by the encoder, the other is the input of the last round. Then we probably will have the second words as output from the decoder. By repeating that process, we will this English sentence will be translated into a Chinese sentence there. So this is how the transformer works. And remember, there are encoder and decoder. However, as we mentioned, and the visual words thing is an analog to the text words in the NLP domain. So in that case, we can adopt the structure of transformer to visual domain. In that case, we don't actually need the decoder part because we don't actually doing something like translation. We don't need a sequence. What we need is a prediction result. However, the encoder part, by transforming the visual words into feature vector, would be very useful. So and this is a vision transformer, a transformer in vision domain, which is quite successful as well. So what they are doing is you can divide each image into patches, like what we have done for many times, and taking each of the patches as a word, as an input for the transformer. And transformer will then generating a original vector representation for that words. This is it. And at the same time, other thing is the position, because the position of each of the patch in the original image makes a lot of sense. So here's another method which can convert the position into another vector as well. So you could actually concate this token representation and the position representation together as a input of the transformer. Then everything goes back to what we have introduced. You have a set of words there, but even right now it's visual words. And then it runs the self-attention for several rounds. And then you could have a final representation for each of the patches there. And these patches can be used as the input for any of the computer vision jobs you need to do. For example, for predicting the classes of the data image, then we could use FC layer or MLP layer to connect to those different feature vector patches to make the final prediction. And you can consider them just some of the fully connected layers will be fine. So anyway, it goes back to what we have introduced. Then you have the final prediction uh, on the image. And this is a vision transformer. And it has borrowed the idea from the NLP domain, but only take the encoder part. But further, it has 80 MLP layer, or more specifically, most of the time it's FC layer there for making the prediction. So this is the major difference between those vision transformer and those text transformer. Okay, that is all for today. I hope you enjoy. Thank you very much.